Hey y'all, it's me, Miss B. Today we're talking about using radians and degree measures and converting between them. So, our first thing we're going to focus on here is measuring angles using degrees. So, we have this thing called standard position, and an angle is in standard position if we have the vertex at the origin and the initial side is on the positive x-axis. So, and something else we are going to talk about is theta. This is theta. That's our new x that we're going to use when we're talking about angles. So here I'm going to have my vertex at the origin, and then I have to have my initial side right here. And then I'm going to have this terminating side. And then my theta is from the initial side to the terminating side, right there. If I have a negative, so that's a positive standard position. Negative standard position is when the angle starts at the origin, or the vertex starts at the origin, and the initial side's on the positive x-axis, but it's going to move clockwise around. So this is theta. So this one, the main thing is counterclockwise. The main thing with this one is it moves clockwise. Okay, so just to review, an acute angle is an angle between 0 degrees and 90 degrees. A right angle is when theta is equal to 90 degrees. An obtuse angle is when theta is between 90 degrees and 180 degrees. And then finally, straight angle is when theta is equal to 180 degrees. Okay, so you can go ahead and cross this out. Okay, so a radian, just a radian, is going, the measure of that is going to be the length of the intercepted arc divided by the radius. So if I have an angle here, this is my center. Here's a radius, and here's a radius. The intercepted arc is the section here. So that is the intercepted arc. What did I do? Why isn't this working? Come on. That's weird. Huh. Well, I don't know why it's not. Oh, because I put white over top of it. Okay. That's very strange. Alright, so that's the intercepted arc. I'll just put a dot next to it since it's not going to highlight. Okay, so then the number of times the diameter of a circle wraps around the circumference is pi, which is 3, well, I shouldn't say equals, I should say about 3.1415 ... because it goes on forever. All right, so the radius of a circle wraps around 2 pi times, which is where we get their circumference is equal to 2 pi r. So 2 pi times the radius gives us our circumference. All right, our radian measure, the way we're going to find that is theta is equal to our s over our r, where s is the intercepted arc and r is the radius. And then an arc length, we just rearrange this equation so that s is equal to r theta. So really today we're focusing on switching back and forth. So let's go ahead and start doing some examples. So this one says find the measure of theta. Let's actually find the measure of let's do arc CD since it's what asked for. And the way we do that is a little CD and then a curve over top. Okay, so I'm looking for the measure of an arc, so that's S equals R theta. So here, my R is equal to 4, and my theta in radians is equal to 1/2. So then my intercepted arc is 2, and we want to label it inches. Pretty easy. So this one asks, if the measure of the central angle is 3 radians and the measure of the intercepted arc is 42 millimeters, what is the measure of OF, that intercepted arc? Go ahead and do that one on your own. So we have our formula, S equals R theta. This time our intercepted arc is 42 and our radius is unknown because our OF is this right here. So, and then our theta is 3. So we divide both sides by 3 and we get that 14 is equal to R. So 14 millimeters is our radius. Or OF, I should say, I guess. Okay, so how many radians are equal to 360 degrees? So this is going to be 2 pi. So radians, again, is the length of the intercepted arc divided by the radius, and so that is why that is 2 pi, because we only have our radius is 1, then we've got 2 pi around. All right, and then 180 degrees is going to be pi. So we have that pi is equal to 180 degrees. This is going to be important for, let me actually write this as pi radians. This is going to be an important conversion rate here. So to convert from degrees to radians, we're going to multiply by pi radians over 180 degrees. And then to go from, oh no, what did I do? Okay. To go from radians to degree, we're going to multiply by 180 degrees over pi radians. Okay, so the reason why we would do that is if it asks for different units than we were given. So a circle has a radius of 10 inches. Find the length of the arc intercepted. by a central angle of 120. So we're looking for our intercepted arc, and S is equal to r theta. Our radius is 10, and our central angle is 120. But we want to multiply by radians. So we have 120 times, well, actually, let's just write this over here. So we have 120 times pi over 180, and this is degrees and radians. So we multiply this out, my degrees are going to cancel, these 10s are going to cancel, so then I have, let's simplify a little bit, so this is going to be 9, let's actually divide by 6 instead of 3, so 3 and 2, dividing 12 and 18 by 6, and so I get that we get 20 pi over 3 radians as our answer. So we always multiply let me, instead of saying multiply, we'll say always need central angle in radians to solve. So that is why we needed that conversion rate, is because we always need that central angle in radians to solve. Okay, so I want you to go ahead and convert the following using those conversion rates up above. Okay, so for 30 degrees, you should have had multiplied by pi over 180, and so you get pi over 6 radians when you simplify. 90 degrees, again, you're multiplying by pi over 180, so we get pi over 2 radians. Negative 135, we end up with negative 3 pi over 4.
This is Tench. Please call 4045.
Okay, so if I were typing this by calculator, I would just type negative 135 over 180, and then I would use the fraction to decimal button, and it'll put it in the least, it'll put it in simplified form for you. Okay, pi over 3 radians, we're going to multiply that by 180 over pi. These pi's cancel. This becomes when we divide by 3, it becomes a 6, so we get 60 degrees. And we need to make sure we label. This next one here, these pi's cancel. We're left with 6. So 60 times negative 5 is negative 300 degrees. Finally, 1 radian. We already know this, but 1 radian times 180 degrees over pi radians. These radians cancel, and so we are left with 180 over pi degrees. Okay, so we're going to start drawing angles here. 1 revolution is equal to 360 degrees, or 2 pi radians. So when I'm graphing, I kind of have to know my unit circle a little bit. So from here to here is 90 degrees. We kind of can see that. So 90 degrees is equal to pi. So we have 0, pi, 2 pi, 3 pi, and 4 pi. Or wait, no, I didn't do that right. Because we're all the way around is 2 pi. So we have 2 pi. So then this is pi over 2, pi, 3 pi over 2. There we go. And so then in between here is pi over 4 halfway. So that is 45 degrees. So I'm going to draw my angle by drawing, remember I have to have it on my terminal side, on my initial side on that positive x-axis, and then that there. So we need to make sure we draw that in, and then we have our arrow pointing this way, and that's theta. 5 pi over 4 is going to be 5 of those, so 1, 2, 3, 4, 5. We're moving in the positive direction, so I'm going to start here and go around this way, and that's theta. For negative 3 pi over 4, we're moving clockwise. So initial side, point at the origin. So then I'm going 1 pi over 4, 2 pi over 4, 3 pi over 4 in the same direction. I'm sorry, in the clockwise direction. Then finally, 9 pi over 4. So I have one start at our terminals. I'm sorry, initial side, point at the origin. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. So we're back here. But the way we write this is it's going to wrap all the way around and then come back here. So it signifies that we've gone around more than once. Okay, so this brings us to our next point. We have two angles with the same initial and terminal sides with different rotations. Those are called coterminal angles. All right, there are infinitely many coterminal angles, and we can find them by adding or subtracting 360 degrees or 2 pi. Okay, so we want to find a positive angle that is coterminal with each of the following. Most of the time when we're finding a positive angle, we're trying to get it between 0 and 2 pi or 0 and 360. There are some examples like this one here where it won't be, but for the most part, that is our goal for graphing. All right, so we've got a 400-degree angle, and so to get it positive but between 0 and 360, we have to subtract 360. And so 400 minus 360 gives us that this angle is 40 degrees. For this next one, we have negative 135 degrees. We add 360 degrees, and so we get that this equals 225 degrees. So negative 135 and 225 are the same angle. This next one, it's not going to be between 0 and 360, but we'll just add 360 since we want it to be positive, and so we get 390 degrees. All right, so this next one down here, we've got 17 pi over 6. So we want to subtract 2 pi. Now one way of doing this is typing 17 over 6 minus 2 in your calculator and getting a fraction and then just sticking 2 pi on it. Or what you can do is you can multiply this by 6 over 6, So we have 17 pi over 6 minus 12 pi over 6. And so we get 5 pi over 6 as that angle. And that is in radians. All right, for this next one, we've got negative pi over 12. We want to add 2 pi to make it positive. Multiply by 12 over 12, so we have a common denominator. So we get that this angle is equal to 23, I don't know how that happened, 23 pi over 12. Go ahead and do this next one on your own. So 13 pi over 5 minus 2 pi, so 13 pi over 5 minus 10 pi over 5 is equal to 3 pi over 5. Okay, so the reason why we want to do this is for graphing. Outside of that, we'll get to solving and things like that. So it's useful graphing, and it's also useful for calculating sine, cosine, tangent, etc. Okay, so let's do some examples of linear and angular speed. These are like our real world examples. They have a lot to do with what's the thing? Physics. Okay, so linear speed is given by well, it's dependent on the side of the circle, but it's also given by v equals s over t. So v is how we talk about our linear speed, and that's going to be in feet per minute and miles per hour. Angular speed is given by this little w, it's not really a w, equals theta over t. However, it is not dependent on the size of a circle. And that's always going to be in radians per something, minute. Most of the time it's going to be radians per minute, but sometimes it'll be otherwise. All right, S, you should know these from before, is arc length, theta is your angle measure, and R is your radius. Oh, and then obviously T is time. Almost lost that one over there. Okay, so let's jump into some examples. It says the hard drive in a computer rotates at 3,600 revolutions per minute. This angular speed expressed in revolutions per minute can also be expressed in radians per minute. So if I have, I'm going to highlight the important information as we should when we do a word problem. So I've got 3,600 revolutions per minute. It tells you its angular speed, but we want to put it into radians per minute. So we need a conversion, and so we're going to ask how many radians are in one revolution. Go ahead and answer that question. There are 2 pi radians in one revolution. So 2 pi radians per revolution, and we're going to multiply that by 3,600 revolutions per minute. Now when we do that, these revolutions cancel, and we are left with 7,200 pi radians per minute. And most of the time, we want to leave stuff in terms of pi. Not in terms of pi, but leave pi. That's an ugly pi. I'm getting carried away here. All right, so in this next example, a wind machine generates electricity. A wind machine used to generate electricity has blades that are 10 feet in length. The propeller is rotating at 4 revolutions per second. Find the linear speed in feet per second of the tips of the blades. So I want you to go ahead and draw a picture. Okay, so you should have drawn something that looks like this. Maybe this is like the blades and them rotating. Here's the center, and then here's a blade, and that's 10 feet long. Okay, so currently we have our information in revolutions per second, but we want to get it into feet per second. So we're going to have to do a conversion here. So we'll go ahead and start with our normal. So we have 4 revolutions per minute. And down here we want to end up in feet per second somehow. And remember that angular speed does not depend on length, but linear speed does. So I'm just going to make a note that linear speed is dependent on size. So easy conversion, minutes to seconds. So if I have 4 revolutions per minute, I'm going to multiply by minutes. 1 minute is 60 seconds. And we know that 1 revolution is 2 pi radians. And then we want to multiply that. So our radius is 10 feet. So then our minutes cancel with minutes, our revolutions cancel with revolutions, and our radians and our radius cancel. And so then we are left with 4 times 2 pi times 10, so 80 pi over 60 seconds, and that's feet per second. So we want to simplify. Did I do that right? Oh, you know what? I made a mistake here. Let's go back. Do. Okay, we're rotating it 4 revolutions per second, and I just converted it to seconds. So we can erase this here. And so this is 4 revolutions per second. Okay, so there's nothing that goes here. We'll just put a 1 for a placeholder. And so then this cancels and this cancels. And so then we just get 80 pi feet per second. So we accidentally put in one too many conversions in there because I misread the problem. It was supposed to be in seconds, not minutes. Okay, so then if you plug that into a calculator, you get that it's about 251 feet per second. This is one of those situations where converting it makes more sense because of the fact that we have our thing. So this is just a reminder that S is equal to r theta. All right, that's all for today, folks.